Welcome to EDU World Space.
Here we're going to be using Gauss's law to find the electric field in different regions around a conductor surrounded by an insulator, both of which hold some charge. And a reminder of what Gauss's law says is it says that the electric field projected onto the area surrounding a region is proportional to the charge enclosed in that region. You almost never do the integral on the left-hand side. You assume a symmetry. Here we've got spherical. And so that electric field is assumed to be constant, normal to the surface. So you can immediately pull out that integral. And here the surface that you're imagining, the Gaussian surface that you imagine, of course, has a symmetry of interest, and it's usually something that you can revise in your mind to have arbitrary dimensions. So you get to choose that side. So usually the problem is finding the enclosed charge, and that can sometimes involve an integral. But we're basically going to use that relationship with the spherical symmetry in order to find the electric field in various regions. And first of all, we'll say inside the conductor. And that is easy because the electric field in electrostatics is zero inside a conductor. And remember how that happens. Charges, if the conductor gets zapped, the charges move quickly to get far apart from each other and to stabilize. So they will zip to the surface and then sit there. R greater than, and I should say less than or equal to R, greater than equal to 2R, we're going to say that that is zero because we are actually going to finagle the Q enclosed to be zero. And I will do that now, is to show you how we are going to make the density inside that insulator just the right amount to cancel the charge in the conductor. So the density times the volume of the insulator plus the Q on the conductor, we're going to revise that to become zero. And so kind of rearranging this formula, we just simply need to find the volume of that insulator. Volume of a sphere, we know that, and we simply have to take the volume of the outer sphere at 2R and subtract from that the volume of the inner sphere at R. Okay, and we know the volume is 4/3 pi R cubed. So we have a pretty simple relationship. Let's see, this is going to be equal to 28 pi R cubed over 3. And so we know what charge, total charge, is enclosed on the outer sphere. And we know its density. Okay, so the hardest electric field to find will be in between the insulator and the outer region, with R kind of sandwiched in between the big R and the twice R. as we'll see, that's not hard. It's just a matter of keeping things organized. So we want to deal with the enclosed charge, which is coming from two places. Okay, so we have a 1 over epsilon. Yeah, we'll put the enclosed charge 2. But that enclosed charge is going to come from two pieces. It's going to come from the rho times the volume of the shell, the Gauss's law shell that we're drawing. And you have to, yeah, I'll show the Gaussian surface there. And then you have to add to that the Q on the conductor. And the volume of the shell can be revised from what we did prior. It'll be the volume at little r minus the volume at big R. So just the part of the insulator that holds that charge. And that's 4/3 pi, little r cubed, minus 4/3 pi, big R cubed. Okay, and then we want to multiply by the density. And I'm going to go ahead and get it in terms of charge Q. So we've already found that density. Yeah, it's kind of ugly looking. Has 28 pi r cubed in the denominator and a 3 upstairs. Let's see. Let's get the 3 in there. Okay, so we can do a little bit of simplifying. And let me see, we have a 1 over 7 and the r, well, no, we don't cancel the r cubed, minus q over 7 big R cubed times r cubed minus big R cubed. Okay, now that might not help us too much. We've got to put that back in with a lot of other constants and solve for the ER. Okay, then we still have the Q over 4 pi r squared epsilon naught. Okay, so the next step is to simplify this down a little bit. And we see that we have two terms that look like 1 over r squared, and one term that goes as r. And I'll just show you what the result is. This is q over 28 pi epsilon naught times 8 over r squared minus r over r cubed. Kind of awkward, but the algebra will work that out. Okay, so what does this look like? The electric field, radial part of the electric field. Let's make a quick sketch. And some interesting things will come out. So there's 0, big R, and to big R. Okay, so the electric field stays zero until it reaches the first surface, and then it jumps up to the value it would have had for point charge Q sitting at the origin. And then it smoothly goes to zero. Now, it doesn't have perfectly zero curvature, but we'll just kind of show it schematically going smoothly to zero, and then it goes to zero and stays there. So one thing that's true about this behavior is that the jump up is indicative of a conductor, whereas the smooth transition, now the derivative of the electric field is not continuous, but the smooth transition to zero is an indicator of an insulator. So we can see those two behaviors quite clearly in our answer.